Hello and welcome back to High Peak Education, and I would like to perform this lecture about rotational motion. I will be focusing on rotational dynamics. Namely, I'll be focusing on how torque is related to rotational inertia and angular acceleration. In previous intuition videos, I have showed how a torque leads to an angular acceleration because torque is our rotational equivalent of force. So I will be showing Newton's second law for rotation. Furthermore, I will be discussing rotational inertia more, and also angular momentum, and then finally rolling motion. Rolling motion can be studied using torque, but I will use the energy perspective and conservation of energy to study rolling motion. So let's go ahead and get started. Let's take a look at Newton's second law for rotation. This we know to be Newton's second law for linear. Net force vector is mass times acceleration vector. We saw that earlier in the course in earlier chapters. We know that dynamics concerns ourselves with how forces affect motion, why things move. So the question is, what is the rotational equivalent? So how does torque, which is our rotational force, relate to angular acceleration? So let us derive the rotational form of Newton's second law. Now, in order to derive this equation that I'm going to show, it's not very difficult. If we assume that torque is coming from a perpendicular lever arm, that is, phi equals 90 degrees, then take this force here, which is net force, and multiply by that lever arm. So then the net force becomes the net torque. Take this right-hand side of the equation, multiply by also the lever arm, and then linear, which is tangential acceleration, is equal to angular acceleration times radius. So what we get is we get mr squared on this side times alpha, and then we get torque on this side, net torque. So if there's a force, and that force is perpendicular to some radius, and it's on a mass, imagine this is a frictionless tabletop. Use the definition of torque, just multiply by a radius, use the definition of alpha, and here is our equation. Torque for a point mass is mr squared times angular acceleration alpha. And for an object composed of many point masses, which would be an extended object, a large solid body, then you add up all the mr squareds, and I here is a counter, and for a rigid object we would have the sum of all the torques, that's the net torque, is equal to the rotational inertia of the object times the angular acceleration alpha. Okay, so notice that if force equals mass times acceleration, and this is net force, then net torque is equal to rotational mass, which is rotational inertia, times angular acceleration. And this is exactly what we would expect. Remember that rotational inertia here depends upon mass and strongly depends upon radius. So when it comes to net torque, it does not just matter what the force is, but where the force is exerted, at what radius, and for that matter, mass is not only important for rotational inertia, but certainly radius as well. So I will perform this example in a later video, as well as this example. Notice that the first example will be a basic motor, seeing how angular acceleration arises from torque and rotational inertia, and we can relate that back to rotational kinematics, and this relates to rotational kinematics as well, and we'll see how Superman and General Zod got along or didn't get along. Let's take a look at rotational work and energy. So the question is this: a spinning object has rotational kinetic energy. We've actually discussed that before. We've said that linear kinetic energy can be converted into rotational kinetic energy if we know that omega is equal to v over r, and we can define rotational inertia. But in order to initiate spinning in an object, rotational work must be done. So consider a tangential force that rotates a rigid object. Imagine that there's some radius to this point, and that there's some angle phi, which is an angle between the ds vector and the radius extended. So I should say that this phi is actually between the radius extended and the force itself, and ds is the perpendicular path that this point should be rotated on if we're going to get maximum torque. So notice that phi, not necessarily being perpendicular to this radius, suggests torque, and so it should make sense to you that the work done rotating for an object from theta initial to theta final is going to be this. Work is equal to the integral from theta initial to theta final of tau d theta. Now notice this looks exactly like the work done for a non-constant force. Hopefully you recall that when we were looking at linear forces, when the force was not necessarily constant with displacement, we had to take the integral from x initial to x final of f dx, because the force could depend upon x. Remember, we interpreted that as the area under the curve of a force versus displacement graph, and that was the net work done by a non-constant force. In this case, the work done by a non-constant torque is the integral from theta initial to theta final of tau d theta, and notice that theta is the rotational equivalent for displacement, and tau is the rotational equivalent for force. Thus, this is what we get for the work kinetic energy theorem for rotation. We get the work done is the change in the rotational kinetic energy. So that's 1/2 I omega final squared minus 1/2 I omega initial squared. I being the rotational inertia, same thing as moment of inertia. Omega being the angular velocity. SI units are radians per second. When you work all those units out, you get joules. Because again, this is energy and work. So I will also show this example in a later video. And this example is probably one of the most difficult examples I will show in an online video, but I will show this example as well. Now, what is the concept of angular momentum? Remember that linear momentum is going to be basically the inertia of motion, mass times velocity. Angular momentum is going to be rotational motion inertia. In other words, if an object is already rotating, how easy or difficult is it to keep it rotating? So, angular momentum is a measure of how much an object that's rotating about an axis will keep rotating. So it's the sort of rotational dynamic equilibrium. Angular momentum increases with rotational inertia, remember the radius dependence, and the angular speed. So if you have a greater rotational inertia, greater rotational mass, and a greater angular speed, which is already a greater amount of motion in terms of rotation, the angular momentum will be larger. Interestingly, given angular momentum definition, it is valid for rigid and non-rigid objects. So it turns out angular momentum is different than torque. Torque is only sort of relative to an axis. And the interesting thing about angular momentum is that it's independent of the rotation axis location. When an entire solid body is rotating, we talk about the angular momentum of that object, independent of where the axis of rotation is. So that's kind of interesting. Now, of course, if an object is unconstrained In other words, if it's not tied down to a rotation axis, objects that are free to rotate will rotate about their center of mass. So it's relatively easy to find the axis of rotation. But it turns out that angular momentum can be defined for a rigid and a non-rigid object. So by the way, because this angular momentum is so flexible, this concept that we're driving towards, the conservation of angular momentum, which is the rotational equivalent of the conservation of momentum, this is actually one of the most fundamental physics properties in the universe, really. And so one thing I want to emphasize is that unless an external torque, a net external torque, acts on the system, the angular momentum of the system remains constant. And again, we call this conservation of angular momentum. In linear, we said that there had to be no external force. Now we say there has to be no external torque to change the angular momentum. So let's have a look at the mathematics here. So a rotating object with no translational motion has no linear momentum, but it does have angular momentum. Angular momentum of a particle relative to an origin with position O, linear momentum p vector, with position vector r vector. Remember, r vector is the position vector drawn with its tail at the origin and its head at some point of interest. If there's a point mass there, then this is its linear momentum, p, and this is the angle phi between the radius extended and the linear momentum vector, we can define the angular momentum vector as the following cross product. L vector is equal to r vector cross p vector. And the direction of this L vector is given by the right-hand rule. So we take our fingers and we point them in the direction of the position vector. We rotate them, so we rotate them in the direction of the linear momentum, that's p vector, and the thumb points in the direction of the angular momentum vector axis, and that's L vector. So L vector here is not a length, it stands for angular momentum. Again, symbol overusage, but we have to deal with it. Now what about the magnitude of this cross product? It should be given by this expression, mvr sine phi. Is that mv is the magnitude of linear momentum, r is the magnitude of the position vector from the origin. And by the way, this origin you can think about as sort of the axis of rotation, sort of where the angular momentum is relative to, and then sine of phi. And again, phi is the smallest angle between r vector and p vector. The units for angular momentum are kilogram meters squared per second. That's the units of mv, that's kilograms times meters per second, times m, meters. Notice that if L equals 0 and phi equals 0, only linear momentum is imparted on an object because the position vector and the position vector and the linear momentum vector are parallel. L is maximum when phi equals 90 degrees, because that means the linear momentum is causing this position vector to be pushed in a perpendicular sense. So that's all maximum angular momentum. Now let's look at the analog of the generalized version form of Newton's second law for angular momentum. So recall that Newton's second law for linear was the sum of the forces is equal to dp vector dt, the change in the linear momentum vector with respect to time. So by analogy, and I'm not going to go through all the mathematics, this is gone through in many textbooks, the sum of all the torques, that is the net torque, is the change in the angular momentum vector with respect to time. So this is exactly analogous to Newton's second law, but just for rotation. So note, the larger an object's linear momentum, the larger the linear force. Show that rotational inertia is large when you have an object that has a large mass at a radius. So you can imagine, say, like a bicycle tire. So why is a bicycle tire so stiff? That is, why does it have so much rotational inertia? Well, it mimics a hoop. Remember, a hoop has all of its mass on the outside. It takes a lot of torque to get the bicycle tire going, but once you get it going, it keeps its angular momentum very well. And that makes the bicycle tire very stable. Its axis of rotation is hard to change the direction of, and for that matter, once it's moving, it keeps moving, keeps rotating. So this is why bicycles are so stable when they're in motion. And think about this. Why does a football quarterback spiral a throw? If a quarterback did not spiral a ball, it could get blown around by the wind, it could have a lot of air resistance, and so on. But if a quarterback spirals a throw, the orientation of the axis should stay relatively constant. And so the ball's trajectory should be relatively stiff, and it should take a pretty nice flight path. Okay? So notice that this is the same reason that basketball players spin a basketball when they shoot it, because again, the rotation of the ball allows it to basically stay on a nice trajectory that's not easily swayed by even small air currents. Because, again, we retain the direction of the axis that the ball is rotating about. So let's talk more about the conservation of angular momentum and its analog to linear momentum. What is the angular momentum of a rigid object? Well, we know that angular momentum is like mvr sine phi. But suppose the object is rotating instead with omega. So suppose the object is rotating, and we know omega is equal to v divided by r, and we also know by introducing that introduces another r, so we get mr squared. Now adding all the mr squareds gives the rotational inertia. So the alternative form for the equation of angular momentum is rotational inertia times angular velocity. Notice that this should be entirely reasonable to you because in linear this is p equals mv. Linear momentum is equal to mass times velocity. Well, this is angular momentum is equal to rotational mass times rotational velocity. So this is what it should be for a rigid object. Now in a previous chapter, we saw that in the absence of external forces, the net force equal to 0, the linear momentum was conserved, that the P in equals the P out. Likewise, in the absence of external torques, where the net torque equals 0, the angular momentum is conserved. That's L in equals L out. So, if there are no external torques, if all the torques are internal, doesn't mean there's no torque in the system. It just means that when you draw a circle around the system, many objects, all the torques go between the objects. That is to say, the change in the angular momentum with respect to time is 0, then the net torque is 0, and the angular momentum is conserved. So L initial equals L final. Remember, these are not lengths. These are angular momentum magnitudes. And that means I initial, omega initial equals I final, omega final. I being the rotational inertia, and omega being the angular velocity. So think about this. If an object suddenly changes its rotational inertia, it should change its angular momentum. So this is a very common demonstration done in a classroom by a professor. They stand on a turntable, and what they do is if they're holding weights in their hand, their angular velocity is small at first, and they have a large radius, so they have a large rotational inertia. Their angular velocity is small, but as soon as they bring the weights inward, they decrease their radius, thus increasing their rotational inertia, decrease their radius, thus decreasing their rotational inertia, and thus their angular velocity increases quite a bit. So rotational inertia is inversely proportional to angular velocity when angular momentum is conserved. So this is a really nice demonstration to observe. Now, by the way, in intuition video I performed earlier, the way you would often see this in the Olympics, the Winter Olympics, is with ice skaters. When they rotate and then they bring their arms inward, they spin faster. And that's because they are getting a greater angular velocity because they have a smaller rotational inertia. So that's exactly what this conservation of angular momentum example demonstrates, and I will show that in a later video. Now here's a question. What about conservation of momentum for collisions? Previously, with linear collisions, we said that we could have elastic or inelastic. Well, what about if a child jumps onto playground equipment? Well, if a child jumps onto playground equipment that's spinning, this is essentially a rotational collision. And so when the child jumps on, there's an increase in the rotational inertia, so there should be a decrease in the angular velocity if the system conserves angular momentum. So that is, if we're just given mass and radii and angular velocity, we should be able to calculate what the final angular velocity is and see what happened to the kinetic energy. Okay, so again, I will perform this example in a later video. I want you to note the analogies between rotation and translation. That is dynamics, energetics, and momenta. Look here. Notice kinetic energy, equilibrium, Newton's second law, momentum, and the conservation principle. These are the equations I recently just went over for rotation, and notice they have very, very analogous looking equations for translation. That is, you see direct correlations between rotational mass I and mass, angular velocity omega and v. You also see torque is like force, and then angular acceleration is like a, the linear acceleration. Capital L vector is like p vector. Angular momentum is like linear momentum. And conservation of angular momentum is like the conservation of linear momentum. Same form of the equations. So this is something that you should be familiar with for this course, for sure. I want to mention a brief word about gyroscopes. Gyroscopes utilize the conservation of angular momentum. How do they do that? Gyroscopes precess, that is, the axis of rotation wobbles, so to say, or rotates around some arc, sweeping out a cone-type shape. Usually the speed of precession is much, much less than the speed of rotation. Now, in an example like this with the top, the force is down, say this weight, so the torque is perpendicular to the current angular momentum that the spinning object has. But notice that that's going to change the direction of the axis, but not the speed of rotation. So a top and even the Earth precess over time. So let's think about what's going on. If you have, let's say, a top, its speed of rotation is quite large. Okay, so it has a large amount of angular momentum. So notice the angular momentum vector is pointing that way given the right-hand rule. We rotate our fingers in the direction that the thing is rotating, and we see the direction of the angular momentum vector. Well, imagine that this angular momentum axis has a force on it. So it has a force on it, in other words, it's a weight force that might cause this thing to tumble down, you might imagine, this mg. But notice this mg, at least in terms of linear forces, is balanced by this normal force. But imagine that we use the right-hand rule and we look for the torque on this top. We take R and we take its cross product with the weight, and notice the thumb points in the direction this way. That's the direction of the torque. Notice the torque is perpendicular to the plane that contains the position vector, the axis of rotation, and the weight and the normal force. So what that means is this top will be spinning very fast, but its axis very slowly will precess around some other axis. And so this is the precession axis, what's shown here, Z, but then here's the angular momentum axis of the spinning object. Notice that this will rotate around very slowly, and it'll sweep over some conical path. Notice that the change in the angular momentum vector is only directional. It's not changing the speed. Now, interestingly enough, Earth, in terms of its climate, over time, precesses. The Earth spins on its axis, but over time, it slowly sweeps out a cone. This happens over, 20,000 years or more. I don't remember what the time scale is, but it's many, many, many thousands of years. And it turns out that right now, the Earth is having its North Pole pointed towards Polaris, which is the North Star. Now, the idea is that in about 10,000 years, or whatever it is, some very long period of time, it'll be pointed away from that North Star. And then another 10,000 years, it'll be pointed towards that North Star. So a very slow precession of Earth's axis of rotation. And by the way, this does affect Earth's climate slowly over time. The last major topic I want to talk about in this lecture is rolling objects. And we're going to study these mostly from the energy perspective. Let's consider what rolling really is. Rolling is an object that rotates along, but also has a linear velocity without any slipping. So it has both translational motion and rotational motion. That is, there's a linear velocity to the center of mass, and there's a spinning velocity to the outer edge. So you can imagine anything that rotates is basically a combination of spinning and movement of the center of mass. So that's what it means to roll. So, what would the total kinetic energy of rolling be? It would be the translational plus the rotational kinetic energy. So that's going to be 1/2 mv of the center of mass squared plus 1/2 I of the center of mass times omega squared. Notice that the center of mass is the point, remember, where we can think of all the mass would be collapsed into for an extended object. Now keep in mind, if you want to simplify this down to one variable or one set of variables, the rotational inertia can be written in terms of mass from a table if you know what the rotational inertia formula is for that extended object that's rotating. And we know the velocity at the center of mass is radius times angular velocity. So you can either replace the velocity of the center of mass in terms of omega, or replace omega as v over r, and v is the velocity of the center of mass. So we use the above expression to substitute for linear tangential velocity when there's no slipping. Now, an interesting point about a rolling object is that if you put a tracer on the outside of a rolling object, you'll see that the center of mass will go in a nice straight line, but a point on the exact outer edge of that rotating object will experience what we call trochoidal motion. And trochoidal motion actually sketches out an interesting shape, an interesting path, which we call a cycloid. And a cycloid is a parametric curve that I'm sure you'll study at some point in your mathematics classes. Okay? You can write the equation for a cycloid, but it's best if it's written as a parametric equation. So what you can do is you can understand this trochoidal motion and this cycloid if instead you think about the edge of the rotating object, I should say the rolling object. The edge of the rolling object is the new axis of rotation. Imagine taking a cylinder or something and then gluing a, sort of like a dowel on the edge. And then if you kind of spun the cylinder on that dowel, it would kind of look like this in terms of how it sort of tumbles over. Well, you could think about the so-called parallel axis theorem to try to figure out the rotation along that other axis. Now, by the way, this parallel axis theorem does not just correspond to rolling objects. Any object that's rotating around an axis that is not at its center of mass can be thought of as the rotational inertia formula from those tables of rotational inertia plus mr squared, as long as we know the mass of the object and we know the radius from the center of mass to the new axis. By the way, the new axis must be parallel to the axis formula we have that goes through the center of mass. So these axes must be parallel to each other. Okay, now so if we use that parallel axis theorem for a rolling object and we allow, again, this point on the edge of the rolling object to be our new rotating axis, that's what we're going to call here the contact point. This makes the total kinetic energy of a rolling object have this form. Kinetic energy total of rolling is 1/2 I parallel. Now I parallel is the moment of inertia about this parallel axis times omega squared. So this cycloid path and this trochoidal motion is like saying, suppose there's a different axis of rotation, really. It's not so much about the center of mass, but it's about some point on the edge. And all the kinetic energy is locked up on that point on the edge, sort of rolling along. So that's this parallel axis theorem, moment of inertia, again, times angular velocity squared. So that means the total kinetic energy can be thought of as pure rotational kinetic energy about this contact point. Now, for rolling objects, let's take a look at these conservation of energy arguments. The conservation of energy considerations can be utilized to study rolling objects. In the absence of non-conservative forces like friction, the total mechanical energy must be conserved. We said that previously in the energy chapters. So, the initial kinetic energy plus the initial gravitational potential energy is equal to the final kinetic energy plus the final gravitational potential energy. By the way, these could be elastic potential energy or something else, but for the sake of this discussion, we'll only focus on gravitational potential energy. So imagine, as an example, we have a rolling object that is, let's say, at rest at the top of a hill, some height h above h equals 0. If you start from rest and you roll that object down an incline height h, an object's kinetic energy is related to its potential energy by this equation. Its initial potential energy is equal to its final kinetic energy. Now in its more full-blown form, that's mgh, initial, is equal to 1/2 m v of the center of mass squared plus 1/2 I of the center of mass omega squared. Now, by the way, this is very powerful because this can solve many problems of objects rolling down hills. Now, one more thing, you would reverse this equation by calling these terms initial and this h final if you wanted the object to go up an incline. So this first example question, which I will perform in a later video, shows this as far as objects going down a hill. And then this later example shows objects going up a hill. So just the two examples there. So that ends this video, and I want to thank you very much for your attention. I ask you to please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. If you like, please leave a comment in this video and I will take a look at it. I look forward to receiving those. Please share this video amongst your social network to continue to grow the channel as well. Thank you for watching High Peak Education. I will see you in the next video.